Hey there. We will discuss about hashing, a core concept in data structure. Let me ask you a quick question to get us started. Have you ever dropped your bag into a cloakroom at an event or hotel? You hand over your bag, and they give you a small ticket with a number. When you're ready to leave, you show them that token, and they instantly find your bag without checking every single one. That little token? That's essentially what we call hashing. Hashing is a method used in computer science to store and retrieve data quickly by assigning a unique number, called a hash value, to each piece of data using a special function. This makes it much faster to find or update information, especially when dealing with large amounts of data. So what exactly is hashing? At its core, hashing is a process of representing input data into a fixed size value or key, usually a number, which represents that data. We give it an input, say, our name, and it spits out a number. That number is like a locker number for our data. Now, let's connect this to the real world again. Think of a dictionary. We want to look up the meaning of elephant. We don't start from A and flip every page until we find it. We jump to the E section and quickly reach it. This is how hashing behaves. Instead of searching sequentially, we jump straight to where the data should be. Before we go further, let's understand what a hash function is. A hash function is a mathematical process or formula that takes input data and generates a unique output, usually a number. It's designed to always return the same output for the same input, and it helps map data to a specific location in a structure like a hash table. Let's go deeper using that cloakroom analogy. Each person gives a bag, which acts as data, to the clerk. The clerk uses a system that is hash function to assign a locker that acts as hash table index to that bag. When the person comes back, instead of checking every locker, they look at their token, which is original input. Apply the same system, or we can say hash function, and go straight to the correct locker. It's fast and efficient, just like how computers access data using hashing. Now, for a good hash function, you want these things. First is, it should be deterministic. This means if you give the same input, you always get the same result. Like, if you write John today and again tomorrow, it should go in the same drawer. No surprises every time you use it. Second is, there should be uniform distribution, which means it should spread the items evenly in all drawers. Imagine if all student files went into the first drawer only. It would be a mess. We want to avoid overcrowding and use all the drawers properly. Third is that it should be fast to compute, which means the function should work quickly. If it takes too long to decide which drawer to use, it's not efficient. Especially when dealing with large data, speed matters. Fourth is minimize collisions. A collision happens when two different things end up in the same drawer. Example, John and John both go into drawer 3. That's bad. A good function should try to avoid this as much as possible. In short, a good hash function is like a smart, fast office assistant that always puts the same file in the same place, uses all drawers evenly, works quickly, doesn't confuse files, that is, achieving no collision scenarios. Now let's talk about hash tables. A hash table is like a giant shelf of lockers. Each slot or compartment is called a bucket or slot. When we insert data, we use the hash function to figure out exactly which slot the data belongs to. For example, if we want to store the names of students in a class, we apply a hash function to each name, and it tells us exactly where to put it in the table. This way, even if we have hundreds or thousands of names, we can access any one of them instantly using the same hash function. Let's see mapping example by a very famous coding problem that is finding duplicates in a list. Say we have a list of numbers and want to find if any number appears more than once. Without hashing, we'd have to compare each number with every other number, which is slow and inefficient. But with hashing, we can create a hash table to keep track of numbers we've seen. As we go through the list, we check if the number is already in the hash table. If yes, it's a duplicate. If not, we add it to the table. That's the power of mapping, quick checks, instant lookups. Understanding collisions. So what are collisions in hashing? Imagine two people coincidentally get the same locker token from the clerk. Now what? That's a collision, basically two pieces of data mapped to the same hash table index. We handle collisions in a few ways. One method is chaining, where each slot holds a list. If multiple items land in the same slot, they're added to the list. Think of it like stacking bags in the same locker. Another method to handle collisions is open addressing. If a slot is full, we look for the next available one. It's like saying, locker 5 is taken. Let's try locker 6. Still full? You simply try locker 7. You basically try until you get the slot. Load factor and resizing. Let's talk about load factor first. Load factor tells us how full our hash table is. It's the ratio of the number of elements stored to the total number of slots. If a hash table is too full, the chances of collisions go up. When the load factor crosses a certain threshold, say 0.7, we usually resize the hash table to make space. Now let's talk about resizing, which means creating a bigger table and reinserting all the existing data using a new hash function or table size. Yes, it's a bit of a heavy operation, but it's worth it to maintain efficiency. Let's explore some common applications of hashing. The first is data storage for key-value pairs, like in dictionaries or maps. These are core to most programming languages and allow quick access to values based on a unique key. Another important use is in database indexing. Hashing helps us perform lightning-fast lookups without having to scan the entire dataset. When it comes to password storage, we never store passwords directly. Instead, we store their hashed versions. This adds a crucial layer of security in case the database gets compromised. Hashing is also used in caching. It helps us store and retrieve frequently accessed data quickly, improving performance dramatically. In compilers and interpreters, hashing is used to efficiently store and retrieve identifiers like variable names and function names. And finally, blockchain technology relies on hashing at its core. Each block in the chain contains a cryptographic hash of the previous block, ensuring data integrity and security. Let's do a mini recap to make sure everything clicks. Hashing turns our data into a numerical representation. Hash tables store data at specific locations decided by the hash function. Good hash functions ensure efficiency and minimize collisions. Collisions are handled using techniques like chaining and open addressing. Load factor tells us when to resize. So hashing is used everywhere, from databases to login systems. So why is hashing so crucial to learn early on? It is because it teaches us to think in terms of mapping, efficiency, and real-world problem solving. We begin to recognize patterns like fast lookups and smart storage that are foundational to building scalable software. By understanding hashing deeply, we're setting ourselves up for success not only in technical interviews, but in real development. This was all for today's lecture. Till then, keep practicing, stay curious, and remember, great software is built on strong fundamentals. Hashing is one of them.